we are going to start a new chapter, chapter 12, thermodynamics. In the last chapter, that is thermal properties of matter, we have studied what is heat, what is temperature, what is change of state, and different properties related to heat and temperature. So this is also a chapter which relates heat, temperature, first law of thermodynamics, the second law of thermodynamics, etc. Okay, now what is thermodynamics? So thermodynamics is a branch of physics which deals with the concept of heat, concept of temperature, and interconversion of heat and other forms of energy. So thermodynamics is a branch of physics which deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. It is a macroscopic science. Why is called macroscopic science? Because it deals with the bulk systems and does not go into the molecular concepts. Okay, here we are considering the pressure, volume, temperature, etc. That is the macroscopic concepts. We are not considering the microscopic molecular description. Okay. In the last chapter, we have studied what is heat and what is temperature. Heat is a form of energy, isn't it? Temperature means it is the hotness or coldness of an object. If whenever there is a change in temperature between two objects, we can say that heat transfer from an object of higher temperature to an object of lower temperature. So heat is something which transferred from an object of higher temperature to an object at a lower temperature. Now we can study some terms relating thermodynamics. First term is thermodynamic system. It is an assembly of extremely large number of particles, atoms or molecules, so that the assembly has certain value of pressure, volume, temperature. A thermodynamic system may exist in the form of solid, liquid or gas or combination of two or more of these. The only condition is that number of particles should be very large. So what is a thermodynamic system? It consists of a large number of particles contained in a system. For example, a cylinder containing large number of gas molecules. So that can be considered as a thermodynamic system. Okay, a petrol engine, petrol gas is taken inside a cylinder. So that is a thermodynamic system. In steam engine, steam taken inside a cylinder, that acts as a thermodynamic system. So thermodynamic system means it is the assembly of large number of atoms or molecules having definite value of pressure, volume and temperature. Okay, and that is called a thermodynamic system. It can be solid state, liquid state or gaseous state. Okay, so that is called a thermodynamic system. The only condition is a system must contain large number of particles. Now, the second term is surroundings. Everything outside the thermodynamic system which has a direct effect on the system is called surrounding. Anything outside the thermodynamic system is called surrounding. For example, a gas contained in a cylinder. So this is a thermodynamic system. Best example for thermodynamic system is a gas contained in a cylinder. So this is a cylinder and it is closed with a frictionless piston. Okay, piston. This is a frictionless piston. Here gas is taken inside a cylinder and it is closed with a frictionless piston. So gas inside the cylinder acts as the system. Here this is the system and anything outside the system is called a surrounding. So surrounding has a direct effect on the system. Okay, surrounding must have direct effect on the system. So anything outside the system is called a surrounding. Clear, children? So what is a system? The system is an assembly of large number of particles and it has definite pressure, definite volume, definite temperature, and anything outside the thermodynamic system is called a surrounding. Now, next term is thermodynamic state variables. A thermodynamic system is completely described by some variables like pressure, volume, temperature, mass, composition, etc. Okay, for example, a thermodynamic system, a gas contained inside a cylinder, okay, provided with a frictionless piston. So how will you represent the properties of the system? The properties or the system is completely described by some variables like pressure of the system, volume of the system, temperature, mass, amount of matter contained inside the system. composition of the system, etc. So such variables are called thermodynamic state variables. Any variables which are used to describe the system completely, such variables are called thermodynamic state variables. These thermodynamic state variables are of two types. First one, extensive thermodynamic state variables and intensive variables. Okay, so thermodynamic state variables are classified into two, extensive and intensive. Extensive means which indicate the size of the thermodynamic system. Okay, the size of the thermodynamics is usually represented by some variables called extensive variables. For example, volume, mass, etc. So volume and mass are the extensive state variables. So next one is intensive state variables. Intensive state variables means which do not indicate the size of the system. Okay, pressure, temperature, etc. are the intensive state variables. Pressure means it does not mean the size of the system. Pressure represents the intensity, the intrinsic property of the system. Okay, such variables are called intensive state variables. Pressure and temperature, density also. Pressure, density, temperature, they are intensive state variables. We can see what is thermodynamic equilibrium. The word equilibrium in mechanics means no force is acting on the system, then we can say that that object is in equilibrium. But in thermodynamics, what is this thermodynamic equilibrium? For example, if a system is said to be in thermodynamic equilibrium if the thermodynamic variables like pressure, volume, temperature, mass, composition, etc. that characterize the system do not change with time. Okay, so if these properties like pressure, volume, temperature, mass, composition, etc. remains constant with time, then we can say that the system is in thermodynamic equilibrium. Okay, so for example, if I consider a gas contained inside a cylinder. So consider a gas placed inside a cylinder. Okay, consider a gas placed inside a cylinder and placed inside a container which is completely evacuated from the surrounding. Let this container is completely evacuated from the surrounding. Now we can say that the pressure, volume, temperature, mass, composition of the gas do not changes with the time because it remains constant, it is completely evacuated from the surrounding. Now we can say that this system is in thermodynamic equilibrium. Is it clear, children? So if a gas is contained inside a insulated cylinder and the cylinder is completely evacuated from the surrounding, this cylinder or this container is completely evacuated from the surrounding. Now the pressure, volume, temperature, mass, composition, etc. remains constant with time. Now we can say that this system is in thermodynamic equilibrium. Consider a gas inside a closed container insulated from the surroundings. Here the pressure, volume, temperature, mass, composition of the gas do not change with time. Here the gas is in thermodynamic equilibrium. Okay, children? Now what is this thermal equilibrium? Two systems are in thermal equilibrium with each other if they have the same temperature. In last chapter we have studied the principle of calorimetry. That means when a hot object and cold object are placed in contact with each other, what happens? Heat transferred from hot body to cold body, finally they attain the same temperature. That means finally they attain thermal equilibrium. Okay, if there is no transfer of heat with the surrounding, heat transferred from hot object to the cold object, finally they attain the thermal equilibrium or they attain the same temperature. So that is called thermal equilibrium. So if one object, two systems are placed in contact with each other, heat can flow from one object to other object and finally they attain a equilibrium position, that is the thermal equilibrium. Clear? So two systems are in thermal equilibrium with each other if they have the same temperature, and that is called thermal equilibrium. Clear? Now we can discuss a very important law of thermodynamics, that is Zeroth law of thermodynamics. Here we can consider three thermodynamic systems. Okay, so A, B and C are three thermodynamic systems. Here A, B, C are three thermodynamic systems, and these systems are completely evacuated from the surrounding. Okay, completely insulated from the surrounding by a wall called adiabatic wall. This is called adiabatic wall. Okay, so this is completely evacuated from the surrounding by an adiabatic wall. Adiabatic wall is a perfectly insulating wall. Okay, it's an insulated wall. And also this adiabatic wall is placed between A and B. Okay, between A and B an adiabatic wall is placed. And A and B are separated from C by another wall, and this wall is called a diathermic wall. This is diathermic wall. Diathermic wall means a completely conducting wall. Okay, so this is the assumption. Consider three thermodynamic systems. What are they? A, B and C. All the three systems are completely insulated by an adiabatic wall. An adiabatic wall means insulated wall from the surrounding. And between A and B placed an adiabatic wall, and AB is completely separated from C by a diathermic wall. Between AC and between BC, what is placed? A diathermic wall, a conducting wall is placed. So what happens? So here consideration, imagine two systems A and B separated by an adiabatic wall or an insulated wall, while each is in contact with the third system C through a diathermic wall or a conducting wall. So what happens when two thermodynamic systems are placed in contact? Heat transfer take place. Between A and C, heat transfer take place. Between B and C also heat transfer take place, because they are separated from A and B are separated from C by a conducting wall or a diathermic wall. So heat transfer take place between AC. Heat transfer take place between BC, and finally they attain thermal equilibrium. Clear, children? So heat transfer take place between A and C. Heat transfer take place between B and C. Finally A and C attain thermal equilibrium, and similarly B and C attain thermal equilibrium. Thermal equilibrium means the temperature remains same. So thus heat transfer take place between the systems until both A and B come to thermal equilibrium with C separately. A comes in thermal equilibrium with C, similarly B comes to thermal equilibrium with C separately. Hence we can write temperature of A and temperature of C are equal, because thermal equilibrium means temperature remains same. So temperature of A and temperature of C becomes equal, and temperature of B and temperature of C becomes equal. TA equal to TC, TB equal to TC separately. What does it mean? This means that this implies that since TA equal to TC, TB equal to TC, this implies that temperature of A and the temperature of the system B are equal. Clear, children? Now next is, suppose the adiabatic wall between A and B is replaced by a diathermic wall, and also C is insulated from A and B by an adiabatic wall. According to the first figure, between A and B what was placed? Adiabatic wall, and between AC and BC what was placed? Diathermic wall. According to the second figure, that adiabatic wall between A and B is replaced by a diathermic wall, and the diathermic wall between AC and BC is replaced by an adiabatic wall. Okay, so what happens? Heat transfer may take place between A and B. But is there any heat transfer take place? No. Why? Because they are already in thermal equilibrium. Okay, so if according to the first one, if TA and TC are equal, TB and TC are equal, that implies that TA and TB are equal. So that means according to the first figure, A is in thermal equilibrium with C, B is in thermal equilibrium with C. That means A and B are in thermal equilibrium. Even if that adiabatic wall is replaced by a diathermic wall, is there any heat transfer take place between A and B? No, because they are already in thermal equilibrium. Okay, so suppose the adiabatic wall between A and B is replaced by a diathermic wall. Also C is insulated from A and B by an adiabatic wall. It is found that the states of A and B change no further, because the temperature remains constant, no transfer or no change of temperature take place, because they are found to be in thermal equilibrium. They are already in thermal equilibrium. And this law is called Zeroth law of thermodynamics. So Zeroth law states that Zeroth law of thermodynamics states that if two systems in thermal equilibrium with a third system separately are in thermal equilibrium. If A is in thermal equilibrium with C, B is in thermal equilibrium with C, what does it imply? A and B are in thermal equilibrium. So if two systems are in thermal equilibrium with a third system separately are in thermal equilibrium. Okay, and this zeroth law was formulated by the scientist R.H. Fowler. So why it is called the zeroth law? Here the scientist R.H. Fowler formulated the law in 1931, long after first and second laws of thermodynamics were stated. But this law is considered to be the basic or fundamental of thermodynamics, and hence it is called zeroth law, and hence it is numbered as zeroth law. Clear, children? So what is zeroth law? If two systems are in thermal equilibrium with the third system separately are in thermal equilibrium. The importance of zeroth law is this law explained the concept of temperature. So thermal equilibrium means in order to attain thermal equilibrium, what is transferred from one system to another? Heat is transferred to keep the temperature constant. Okay, so zeroth law of thermodynamics gives the concept of temperature. Now we can discuss the difference between heat, work and internal energy. What is the relation between them? Heat and work are the terms used to describe energy in the process of heat transfer. Now what is the relation with internal energy? What is internal energy actually? Internal energy is usually represented by the capital letter U. The energy possessed by the system due to the molecular motion and molecular configuration. Okay, so if you consider thermodynamic system, gas contained inside a cylinder. Here the molecules are in constant motion. Okay, so due to the velocity of the molecule, it has energy. That energy is the kinetic energy. Okay, so total kinetic energy of the molecules. Now, if the molecule collide with each other, collide with the walls of the container, it has potential energy. Due to the collision, it has potential energy. Okay, so it has both kinetic energy. Molecules have both kinetic energy and potential energy. So total kinetic energy and potential energy of all the molecules inside the system, that is called the internal energy. So what is the definition of internal energy? Internal energy is the sum of kinetic and potential energies of the molecules of the system. Okay, so it is a sum of kinetic and potential energies of the molecules of the system, that is called the internal energy. The total kinetic energy and total potential energy of all the molecules of a thermodynamic system is called the internal energy. Now, what are the ways by which the internal energy can be varied? What are the ways of changing internal energy? Okay, so first one, if a thermodynamic system, that means a gas contained inside a cylinder provided with a frictionless piston, that is the best thermodynamic system. If the system is placed in contact with the hot body, okay, if it is placed in contact with the hot body, what happens? Heat transfer from the hot body to the system. Okay, that system absorbs the quantity of heat, and what happens to the kinetic energy of the molecule? Kinetic energy increases, and hence the internal energy of the thermodynamic system increases. Okay, so first way of increasing the internal energy is apply heat to the system. Or again, if the system is placed in contact with the cold body, what happens? Heat transfer from the system to the cold body. Again, what happens to internal energy? Internal energy decreases. So what is the first way of changing the internal energy? By applying heat or by absorbing the quantity of heat from the system. Is it clear, children? So if the object is placed in contact with the hot body, or if the system is placed in contact with the cold body, what happens? Internal energy changes, either increase or decrease. That's the first method. Second one, if the piston is pushed down. Piston means here a thermodynamic system means a gas contained inside a cylinder provided with a frictionless piston, that you know. If the piston is pushed down, means what happens? The molecular collision increases, and hence the kinetic energy increases, and hence internal energy increases. So if piston is pushed down means work is done on the gas. Okay, piston is pushed down means we have to do some work is done on the gas. So in that case also internal energy varies or internal energy increases. Or if the piston is pushed up, then what happens? Work is done by the gas. If piston is pushed down means work is done on the gas. If the piston is pushed up means work is done by the gas, then also internal energy varies. Okay, so by doing some work or by applying the quantity of heat, internal energy varies. So what is the relation between internal energy, heat and work? heat and work are the two different modes to change the internal energy. Okay, so that's the relation between heat, work and internal energy. Heat and work are used to vary the internal energy. So that is the relation. Okay, in order to change the internal energy, we have to apply quantity of heat or we have to absorb the quantity of heat, we have to do some work on the system or by the system, then internal energy varies. So thus heat and work are the two modes to vary the internal energy of the system.